Hi everyone, I'm Serge. I'm from University of Virginia, and I've been working here and there with Chisel for the last maybe 2 years. We were working on a chip, and I got interested in cryptography as well, and I thought I'm going to take a look and maybe implement something that's missing, that I think is missing. So the motivation for this work, the way I see it is, I think for RISC-V and RISC-V systems to really grow a lot, I think crypto is something that's required for developers to have, to just grab and use or adapt something that exists. And I think they have to be efficient in terms of power, in terms of performance per watt. And they have to be secure, so we have to ensure that they work well and they cannot be attacked and compromised. And they have to be flexible. It has to be easy to parameterize them, either pipelined or small in area or only one key or more keys and so on. And one example, a recent paper shows that, well, I think Chisel and RISC-V matches very well with IoTs, and you want a device to connect with the cloud or with a host via a medium that you don't really have control of, and that's where you use DTLS, and it consists of AES and elastic curve cryptography and SHA, and mostly it's ECC actually, but all these three I think should be there, available as a library. And I think this is also a great opportunity for a community to actually develop an IP, a crypto IP that's not hidden, not really just all secret, and usually the community in this domain finds vulnerabilities. That's the research. Oh, I found the bug, or I found how to exploit. And it would be greater if we could actually construct rather than just like find some mistake in some work. So I think this is a great research in the future. So I've been working on AES and started also doing some work on SHA. And a basic overview of AES is here. AES is a fixed standard already. It doesn't really change anymore. It's been there for a while, and it's believed to be secure and uncompromised, or mathematically no one showed that they can crack it. And it's a symmetric cipher, so you use the same key to encrypt and decrypt. And yeah, you push a key and a plain text and get a cipher text, and the other way around. So my implementation is kind of basic. I have a top module, AES, that consists of a cipher and an inverse cipher, like that. And each of them has the required algorithm blocks inside. So you have the sub-bytes, the shift rows, mixed columns, add round key, and on the inverse cipher, the other way around, the reverse order. And you repeat that for the required number of rounds. So that's basically how AES works. It doesn't compress the data, it just scrambles it, does some replacement of it, or just mix the data, mix the bytes among the order of the bytes and so on. And the key is a certain length, and then you expand that key into a number of other keys, and you use each of those keys at each round. So that's how AES works. And there is, in hardware, I believe there is no reason to have an expansion implemented in hardware, although it is possible and it should be added. But in my implementation, I have a memory block where the user would write the expanded key already, and the cipher and the inverse cipher would just use it for as long as needed, and then the key can be replaced by another key if needed. So I think that's more efficient in terms of power as well, and also resources. It's easy to have just a piece of memory. This work is available on GitHub. It's open source released, and I hope that some of you will actually look at it and either use it or maybe contribute or give me some feedback. And the files are not just, basically every single file also has a tester. So yeah, that's quite great. Here is a look inside at the signals, so it's pretty involved already. This is the top module, the AES top, which consists of the cipher, the inverse cipher, and the memory block. And the top signals there is the input, and the first section is I send the expanded key, and then it's 15 of them. No, wait, 14, sorry. It's the original one plus 14 more, and the 16th one is just stays zero, stays empty. Then next I have an encryption load and then a decryption load. And it's not perfect. There are a couple of bugs. Like I think the stage should not have been outputted every single clock cycle, but it's there. For the encrypt, it's not there, but for the decrypt, I guess I missed the check. So I evaluated a bit the performance, and I used these simple low-end FPGA boards, mostly because we have them and we use them for the class, and hopefully we will use Chisel in the FPGA lab. So we want them to use these boards with Chisel on them and with AES and SHA and so on. And I didn't use Yosys, I should do that, but I used Quartus and Vivado. So here's some results of synthesis on the Atlas-SOC, D0 nano SOC, using Quartus. So first of all, here's the utilization. The numbers are more or less the same order. They're very close. The implementations are not really bit-to-bit, one-to-one. I use a memory block in the Verilog implementation, which is the implementation done by Altera Cookbook. So I just took that. I like the Altera Cookbook implementation of AES. It's very elegant. And it's actually a pipeline, so this is only for one round. This is like the average utilization per round. So in that case, you would have to add them. So the last result there is the sum of those previous two. The results are pretty close in terms of ALMs and the registers, and also for the Fmax, we see that Chisel is kind of in between. Not sure why the inverse cipher is slower. The mixed columns step has more XORs, and I think that's where that limitation, that slowdown comes. Similarly, on the PYNQ board with Vivado, I have the Chisel results with lookup tables and flip-flops and VRAM. And I also made the Vivado high-level synthesis C implementation of AES. And we see that the utilization is a bit higher. I tried to make it as small as possible, and that's what I got. So yay to Chisel. And we have the same Altera Cookbook implementation, cipher and inverse cipher. So this was both cipher and inverse cipher as AES module together, and those are just the cipher and the inverse cipher separately. And similarly, we have the Fmax, and well, for HLS, I just set the frequency to be the same that I received from Chisel, so that I have the utilization comparison. But yeah, we see that the Altera one runs faster a bit. The Verilog version, not much faster though. So the numbers are very similar, very great in terms of we achieved the same, we did more or less the same utilization and maximum frequency, like operational frequency. It's not really directly one-to-one saying that since we have less number of lines of code, the language is better, but there is a relation there. So I counted the number of lines of code. How easy is it for a developer to implement? And I implemented all of this except the Verilog. The Verilog, I got it from the Altera Cookbook. And well, Python was the shortest, and you see that Verilog is twice longer than Chisel. That was a number that I was surprised by. So writing Chisel is twice faster if the number of lines of code says something. So it definitely means that development productivity is higher, and for a security library or for a security module, that's important, because if a feature is found to be compromised, we can react fast if we have the option to remotely update it over the air. Then we can implement a fix and send an update. I'm working currently on these 3 features. They are more or less done. I should push them. I have a very basic LFSR-based noise generation that is attempting to be a side channel attack prevention mechanism. And I have a pipeline structure as well for the AES implementation. And instead of using just read the values for the XOR, for the mixed column step, I can also compute them on the fly, if that's better, if memory is an issue. Further work, I'm also working on the interfaces, but I'm quite excited about executing a verification step. And I read a paper recently from Carve that is exactly on this topic, system-level formal verification and reasoning on a security module, like on a cryptography module. So I think this is an exciting area of research. Also, I'm working on SHA. I started just with the first with MD0 and SHA-0. And SHA is evolving, probably even SHA-3 maybe at some point will be compromised. We already know that there are attacks for SHA-0, SHA-1, and so on. So these are evolving hash algorithms, and they still have something in common with the older ones, but they are not so recognizable anymore. And one implementation I'm excited about is actually the ECC, since a lot of governments or companies use different curves, and there are always curves that are considered better or newer curves appearing. So being able to use Chisel to have support for a large number of curves to generate flexible implementations of elliptic curves will be, I think, a very useful module for IoT communication. So I believe that this is a great area to work on and to have a useful library in Chisel. So I think I'm all the time. Yeah, thanks.
Does anyone have any questions? So do you think the groundwork you've laid so far will make it easier for you to build SHA on top of your library? Do you think the work you've done with AES, do you think that'll make it easier for you to implement new algorithms? Or is there not a lot of shared code between them?
It's not very reusable, but I got better at Chisel, so that would be nice. But yeah, it's not similar to AES. Yeah.
Great, thanks.
Thank you.
All right, our final talk in the session is